The world is moving towards decarbonization with climate change on the rise, as well as decreasing materials to actually produce the energy, such as fossil fuels. It is expected that nuclear energy will need to increase its capacity by at least 50% by 2050 to meet both the increasing energy needs of the world as well as replacing current fossil fuel sources. Our project, Uranium Project, is taking a patent with 3 reactors that is converting uranium hexafluoride gas into uranium dioxide powder. Uranium dioxide powder is what's actually used in the fuel pellets for nuclear reactors, but our system is just converting the materials, not actually pressing them into the fuel pellets. So, our goal is to reduce the complexity of the system by making it a single reactor instead of 3 reactors. In addition to this, we need to meet Department of Energy requirements for the fuel's purity, as well as managing byproducts of our reactions that are dangerous to employees, either for corrosive reasons or for fissile material reasons.
Our process starts out with uranium hexafluoride, hydrogen, and steam.
UF6 is transported to the facility in pre-made containers in its solid state. The UF6 is heated within its container to turn into its gaseous state, which can then react with the 2 other gaseous reactants.
And they are fed into our reactor in concentric cylinders. And this is at 850 Kelvin, and they're allowed to reach equilibrium. And the solid products will fall into the bottom of the reactor, which includes our uranium dioxide, and then gaseous products will be vented out of the reactor. The solid products at the bottom of the reactor are collected via a solids trap, and this is how we get our final product. These reactions are exothermic, so we need a cooling jacket on the outside of the reactor. And this also provides nuclear shielding based on DOE standards.
The gas vented out of the reactor is then fed into a dry scrubber where hydrofluoric acid is removed in order to drive forward equilibrium. Before entering the scrubber, it goes through a heat exchanger where it's cooled in order to not melt the filter. The filter of the scrubber is made out of a calcium hydroxide material where it reacts with hydrofluoric acid to form a safer solid, since hydrofluoric acid is highly corrosive. The solid material is removed from the filter using a backwash system in order to extend the life of the filter. The gas exiting the scrubber is then sent through a condenser where water is removed. The materials from the condenser feed into a knockout drum where the water is combined with utility water to enter the cooling jacket of the reactor, and the gas is recycled into the reactor to mitigate waste. In an emergency situation, 3 scrubbers will be ran in parallel in order to handle the full flow capacity of the system. The gaseous waste will be sent to containment. The process has strict material requirements due to the nature of uranium and hydrofluoric acid. This meant that in our process, any piping or unit operations that come in contact with hydrofluoric acid or uranium must be coated in Manil 400.
Compared to the patent design of 3 reactors, our design included the 1, and in looking at the results, there was a difference in the percent conversion of the UO2. In the 3-reactor system, it was 90% conversion, but in our system of 1 reactor, we had 98.56% conversion. Now, this is a very good result, and what helped it was using less material, a jacket, and a recycle stream. Now, of course, there is a reason that the patent uses 3 reactors, and that is mainly because of fluoride contamination, which in our system, there was a higher amount in the final product. But this can easily be mitigated and in the further processing steps be removed before converting our powder into pellets.
Economic analysis was performed using Warren Sider's textbook, Product and Process Design Principles. The total bare module cost accounts for both direct and indirect expenses for purchasing and installing pieces of equipment. So our total bare module costs will be $40.8 million. Yearly revenue was calculated using the raw costs of all reactants and the selling price of our final product. The raw material costs were calculated to be $4.37 million. Then product revenue from our main product, uranium dioxide, as well as the resellable byproduct of calcium fluoride, was determined to be $535.16 million. After accounting for both the raw materials and products, the yearly revenue of the plant should be $530.79 million. The total production cost accounts for costs such as depreciation of equipment value, other maintenance costs that are not included in labor, as well as the cost of manufacturing, property taxes, and other costs. Our calculations determined that the total production costs would be $105.8 million per year. The overall period of operation for our chemical plant would be 15 years. 5 of these years would be startup costs and time to build the plant with no salvage value due to radiation contamination concerns as well as corrosion concerns. Overall, the total investor rate of return was 97%. Our process has a lot of risks associated with it for investors. We're dealing with corrosive and radioactive chemicals that endangers workers if not handled properly. The investor rate of return should not be over 100% due to these concerns, but it should still be high because of the high selling price of our product, so 97% makes sense.
The overall goal of our project was to minimize an existing patent of a 3-reactor system to make uranium dioxide powder into a single reactor system. The only materials needed to make this reaction happen are UF6, water, and hydrogen. For every mole of UF6 that goes into the reactor, it reacts with 98.56% conversion, which is much higher than our patent, which we definitely improved upon. The 2 biggest hazards we had in this project was dealing with fissile material as well as corrosive byproducts. Uranium itself is fissile, however, there is not an actual nuclear reaction occurring within our system, which mitigates a lot of safety considerations. HF was mitigated with many safety considerations, such as using a gas scrubber to turn it into a solid product that can safely be handled. In addition to this, the solid product that HF is converted into can also be resold at a higher value than hydrofluoric acid. Because of this, our overall investor rate of return for our overall plant is about 97%. We would recommend that someone go forward with this idea in the future. However, further analysis should be done. These results are very preliminary, and further analysis by experts in industry should be performed, as well as experimental testing to make sure everything is safe and can be implemented at a large scale. In addition to this, other processes could be added after the uranium dioxide that is produced from our process. For example, you could add a system to remove fluoride contaminants from the solid product, and after that, you could add a system to press the remaining UO2 powder into nuclear fuel pellets.